Before we start with topology, I want to finish the series on limits by wrapping up with the limit definition of continuity, which works fine in the context of real numbers and hence undergraduate calculus, but as I showed in the last video, it breaks down if we try to rigorously move forward with calculus using only that definition. So this video is going to be still within the context of undergrad calculus, meaning only real numbers. In an undergrad calculus textbook, the section on continuity usually ends with a description of the Intermediate Value Theorem, which, as I showed last time, the book simply states that proving the theorem is too hard for an undergrad calculus class. So we'll pick up with the Intermediate Value Theorem next video. One additional comment. We tend to talk about higher math as, quote, generalizations of our, quote, real numbers, meaning actual concrete numbers, the counting numbers and addition, multiplication, integers, rationals, reals, and so on. But I think it's useful to observe that one could argue that the opposite is actually true. It's not a generalization at all. The abstractions are derived from the real actual numbers. What I mean is that when mathematicians work to create abstractions such as groups and fields and topological spaces, metric spaces, and so on, they're always describing the real world in an abstract way. For instance, if you were to define fields from scratch, why in the world would you make it so you can't divide by 0 and the multiplicative operation doesn't actually make a group because there's no multiplicative inverse of 0? That's just messy and weird. The reason abstract fields are defined the way they are is they have to be so the definition fits the real, messy world. So in a way, when we talk about abstracting definitions, remember that we're always talking about the real world in an abstract way. So topological spaces, for instance, are not some bizarre higher math construction that's completely inaccessible to us normal humans. On the contrary, it's only an abstraction of the real world. So it's important to be familiar with the real world applications, meaning calculus and the normal undergrad definition of continuity before we move on to the abstract topological definitions, because this real world is where the abstractions come from. So the basic concept of continuity is very intuitive and it's almost too obvious to discuss. We've been looking at limits. What is the value of f of x as x approaches a? Now, frequently, we've seen this in earlier videos, frequently you can find this value simply by plugging a into the function. Functions with this property, that the function at the point a equals the limit as x approaches a, is called continuous at a. It just means what the word means in everyday language, that the function is continuous at a if it's, continuous, as opposed to, say, the Heaviside function, which is 0 when x is less than 0, and then it jumps up to 1 when x is greater than 0. So this is not continuous over real numbers. Okay, so the definition of continuity. A function f is continuous at a if the limit of f of x as x approaches a equals f of a. That's all there is to it. So notice, though, there's a lot hidden in here. This definition implicitly requires 3 things, actually. So first is that f of a is defined, in other words, that a is in the domain of f. The second is that the limit, in fact, exists, which means that f has to be defined on an interval around a. So if this is a, then it has to be defined in an interval. And then finally, that the limit at, or that the value at f equals the limit as x approaches f. So the definition says that f is continuous at a if f of x approaches f of a as x approaches a. So what this means is that a continuous function f has the property that a small change in x produces only a small change in f, okay? So that's all we're saying, is that if you change it a little bit here, you're changing it a little bit here. And then in fact, of course, changes to f of x can be kept as small as possible if you just make the change in x sufficiently small. That's the whole point of epsilon and delta. Intuitively, continuous just means that the function has no break in it. You can draw the graph without lifting your pen from the paper. If you think back to our discussion of parameterizing curves and etch-a-sketches, this was exactly the conclusion that we reached then. If you have two continuous functions, then the resulting path must be continuous as well. So discontinuities. If f is defined near a, that is, it's defined on an open interval containing a except possibly at a itself, then if f is not continuous at a, we say that f is discontinuous at a, or that f has a discontinuity at a. Okay, so there are different kinds of discontinuities that we should be aware of. If we just draw a little function here. So here at a equals 1, there's just a space missing in the graph. So f is discontinuous at 1 because f of 1 is not defined, right? Here f of 5 is defined, but the limit from the left doesn't equal the limit from the right, so the limit doesn't exist here. So f is discontinuous here as well. And then where f equals 3, f of 3 is defined, and the limit as f approaches 3 is also defined, but the limit as f approaches 3 doesn't equal what f equals at 3. So these two are not equal. The limit as x approaches 3 of f of x does not equal f of 3. So this one's a discontinuity too. So these you can see just by looking at the graph. What if we look at the functions instead? What can we see when they're discontinuous? Let's say that f of x equals. So here we can just see that this function isn't defined when x equals 2. X isn't in the domain. So f has to be discontinuous at f. And we can tell here, and we're going to get to this in a minute, but we can tell that it is continuous everywhere else, but it's not continuous at x equals 2. What about... So with this one, f of x is defined everywhere, because it's not defined here with 1 over, this would be 1 over 0, but we do just define it as 1 when x equals 0. So f of 0 is defined, but the limit, this, does not exist because it equals infinity. So here, even though the function is defined at x equals 0, the limit of f of x at x equals 0 does not exist. So this function is not continuous either. And of course, it's kind of interesting because it goes up on either side, but then at 0, it's just 1, right? So it like goes up to infinity just right next to 0, but then at 0 it jumps back down to 1 and then jumps back up. What about... So here we can factor this into x minus 2, x plus 1, and then over x minus 2, those cancel, and we have x plus 1. So with this function, the function is defined at 2, it equals 1, and the limit exists at x equals 2 because the limit as x approaches 2 is going to be 3. But the problem here is that the limit as x approaches 2 of f of x does not equal f of 2, right? Because the limit is 3, but the value at 2 is 1. So 3 doesn't equal 1. So there's a discontinuity here too, and I'm not sure what the graph looks like, but it's something like probably this with like a space there and then a spot down there. And then finally, what about the greatest integer function? Well, we know what this looks like. It looks like you just basically lop off the fraction and it's the whole integer. So like 0.5 equals 0, 1.5 equals 1, and so on. So this has discontinuities at all the integers because the limit from the left doesn't equal the limit from the right. This one and this one are called removable because you can just fill them in with a spot. If you just make the function right there equal 3, then you're done. And if this one is 3, then you're done. So those are removable. This is called an infinite discontinuity. And these are called jump continuities, where the function jumps from one value to the next, and they can't be repaired by simply filling in the gap. So those are the three kinds of discontinuities. And then, of course, I mean, there's sort of two kinds here, because this one, it's not defined, and here it is defined, it just doesn't match. Okay. Now, one-sided continuity. This is something that we actually talked about in our video about the fundamental theorem of calculus, because in order to prove the fundamental theorem, we could prove the function, like if it was on an interval here, we could prove that it was true for the open interval, and then we had to prove that it was true at either end too, and we had to use one-sided continuity in order to prove that. So the definition of one-sided continuity is a function f is continuous from the right at a number a if the limit as x approaches a from the right of f of x equals f of a, and f is continuous from the left at a if the limit of f of x as x approaches a from the left equals f of a. So we look at the greatest integer function. At each integer, this function is continuous from the right, but it's not continuous from the left. So the limit as x approaches n from the right equals n, so n equals f of n. But the limit of f of x as you approach from the left is n minus 1, right? Because like here, for instance, n here is 1, but the limit, the value of f of x coming at it this way is still 0. So it's n minus 1, and then it jumps at f of n. So f of n it's 1, but as you approach, it's n minus 1. So it's discontinuous from the left. It's continuous from the right, but it's discontinuous from the left. Okay. Next. So a function f is continuous on an interval if it is continuous at every number in the interval. And then if it's defined only on one side of an endpoint, we understand continuous at the endpoint to mean continuous from the right or from the left. If it's only defined on one side of an endpoint, it's still considered to be continuous at the endpoint. But what we mean there is that it's just continuous from the right or continuous from the left. And this is important because it's important to remember that we actually defined continuous, that you can't say, for instance, the real numbers are continuous or the rational numbers are continuous. The definition of continuous is a definition about functions. It's not about number systems or number lines. So a function is continuous at a point. And then if it's continuous on an interval, that it's continuous on every point in that interval. So really continuous, it's a property of the function at a particular point, and then you can expand that a little bit by saying that it's continuous on every point in the range, or in the interval. So let's show that the function 1 minus the square root of 1 minus x squared is continuous from minus 1 to 1. So if we look first at the open interval, so if we look when a is between 1 and negative 1, then we can use the limit laws. So we can use subtraction and then the constant rule to say that this equals 1 minus the limit of 1 minus x squared, and then the root law, 1 minus the square root, and then we can do it again. The limit of 1 is 1 minus the limit of x squared. And then the power law says that the limit as x approaches a of a power of x equals the power of the number. So we have that this equals 1 minus the square root of 1 minus a squared. And this is what we would get if we simply plugged a into this function, right? So that equals f of a. So that means that for any value of a between minus 1 and 1, we just showed that it is continuous. And then for the endpoints, we have to be a little more careful about writing it down. So then we also need to prove that the limit as x approaches minus 1 from the right of f of x equals f of a, or in this case equals minus 1. And then also the limit as x approaches 1 from the left of f of x equals f of 1. But you can just go through the same thing and you'll verify that these are both true as well. So doing that will have shown that it's continuous on both endpoints and also in the middle. So yes, this function is continuous from in this closed interval. And again, this is one of those examples that I was talking about back when we were looking at the fundamental theorem of calculus, that it's all about these endpoints. So you've got to be careful about them. And as I said then, try to focus on the endpoints, because I have a real tendency to get bored with these little details and skip over them. But I think the thing to do instead is to focus your interest on the endpoints, on the unusual cases, because that's where it matters. What matters is what's happening at these endpoints, because the middle part is sort of easy, but then the endpoints is where maybe it's a little weird. In this case, you can do it easily. It's the same way. But just remember that anytime there's some seemingly arbitrary detail in a definition or in the assumptions of a theorem, there's a reason they're there and they matter. They're what make the theorem possible. They're not just thrown in arbitrarily. So what this is actually the lower half of a circle. And you can see that. We can just manipulate a little bit. And this is just a circle with the y-axis offset by 1. Okay, I think now's a good place to stop this video. We still have some stuff to cover relating to real continuity. We still need to develop some rules and theorems relating to continuity that allow us to combine simple continuous functions into more complicated ones. We'll do that next week. Thank you. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.